Right, good morning, everyone. Welcome back. We have another session starting on offline reinforcement learning, multi-agent interaction and decision-making. And I'm very pleased to introduce Xianyuan from Tsinghua University, who's going to talk to us about real-world deployable data-driven reinforcement learning. Thank you.
Hi everyone, and thank you. Okay. Hi everyone, very glad to be here to share some of our work on how to develop and deploy a real-world data-driven RL to actually solve difficult world problems. Okay. Thanks. Well, yes. Yeah. Okay. Can you hear me now? Yeah. Okay. So let's get started. So before I introduce any technical contents, I'd like to first share a story that how I actually started doing this type of research. So, well, it actually dates back to 2018, where I just got my PhD and started work. And at that time, basically, a senior manager in a major energy company in China actually reach out to us and say, hey, we have a problem. Can you actually use AI to help us to solve a problem that has troubled us for maybe several decades? Problem is actually to optimize the combustion control of the thermal generating units. So this is an extremely complex problem. By the way, do not know that at that time. So basically, we thought it's interesting problem, very challenging, and seems to have a lot of societal and environmental impact. So we take the project immediately. And when you're just very young and just get a PhD, and you might be more confident and over ambitious. And after we dive into problem, actually we find that we're cooked because we're so cooked because the problem is super hard. So it's like you generate electricity and through a thermal power generating units, and the process is like this. So you have the coal, and then you just crush it and pulverize into a tiny ashes, and then you blow that with a wind into a massive boiler, and the boiler maybe has a height of maybe a 10-story building, and then you need to inject coal and air through maybe 20 to 48 different locations, and then you need to ensure they are poured together and form a huge fireball just in the center of the boiler. And you need to carefully control the water, the wind, and the coal, and everything needs to be just right to actually maximize the combustion efficiency. So the problem is super hard, and the whole system, you have to optimize everything together, because otherwise you cannot maximize the combustion efficiency of this entire system. And the entire system has about over 10,000 sensors and has about almost 70 to maybe 10 different TGUs. Basically, there has 70 or more than 100 control variables. Mostly of them are continuous variables, and you have tons of the cyclic agents. And this is also a typical synchronous decision-making task, because you need to achieve long-term control to optimize the combustion efficiency while reducing the nitrogen dioxide emission. So super hard. And at that time, we have a lot of uncertainty. But one thing we want to do is we want to use RL to solve this one, because at that time, RL is very sexy, and you just have this RL to achieve superhuman performance in a lot of domains. Seems very promising. But we do notice that at that time, so basically a lot of people are actually complaining deep RL doesn't work with the real world. So a lot of people are saying maybe the deep RL heat reinforcement learning doesn't work yet. Some people even saying the deep RL is a waste of time. And some people even joke that almost 70% of the time deep RL doesn't work. So why is that? If you look at some of the real world applications, and we will notice that it's very different from the typical RL tasks we actually solve, maybe in the AI community or actually some of the lab environment. So basically, typical formalism, we interact with the environment, or we have a perfect simulation, we can actually do interact without any restriction. But in the real world case, firstly, many of the mission critical systems, we do not have this kind of simulation, or even you cannot even build a simulator that is accurate enough for you to the transferable policy. And also, it is not possible to directly interact with the system during training. And sometimes even the designing reward is very challenging because the task you're optimizing can be complex. And you are not only need to optimize the reward, you also need to satisfy constraints. So that actually makes the deploying RL or some of the capacity control as well as other tasks were very challenging. Because especially we do not have any kind of simulation. So that actually, but one thing we do have is like we have some of the often data set from the historical operation process of this kind of real world systems. So actually that is something we can leverage, we can optimize the policy to do the control to the optimization. But this actually requires some of the new type of RL, for example, off RL to solve this problem. So that is actually exactly what we do when we solve this problem. We actually collect 1 or 2 years historical data from how to generate from how plots, and in our initial version of our model, so we use some data to train a data-driven simulator, which is the patterns model. But in the later version, we actually remove this one. We use all three of them. We use all ones to actually learn policy, and after the learn policy, we do the open control. So that's the work. Yeah, at least in the open loop setting. So basically, we actually deploy the system to deploy the control loops in the protocols. And then we ask the operators to follow the control suggestions given our policy to do the modification on the control. So we actually find that actually did improve the thermal power combustion efficiency by at least 0.5%. So the number of loops are small, but actually it means a lot for the thermal power industry because the modern TGU's combustion efficiency is around 92% to 94%. Even increasing a little bit, that is extremely hard. But using RL, we can actually improve 0.5%. That is equivalent to save about 3,000 tons of coal a year. And we test on different thermal power plants, and we also turn it into a product. Right now, this system has already been deployed in 6 large coal-fired power plants in China and TGUs. And seems to be happy ending, but actually we learned a lot from this process. And currently, actually, I'm looking back, I'm still in some sense not very satisfied with this work because at that time we can only achieve open control. That is, we provide suggestions and human operators that do the last mile control. We also actually realized that at that time the off-RL methods are far from mature. And if you need to make it work, you need to add a lot of engineering efforts to prevent it from sometimes outputting some of the crazy actions. And but we do realize that this kind of method can be very promising and to solve a lot of real-world physical tasks, and especially in the real-world industrial control. And meanwhile, we realize that there is tons of research need to be done in order to make this type of methods really applicable or useful in real-world settings. That's why it's like from 2018 to 2020, we finished this work and we went back to theoretical and algorithmic research. And the last 2 years, we started again applying some of the methods to solve real-world problems. And this time, we can achieve closed loop control for thousands of hours without any problem. Yeah. And so next slide is we will begin to talk about some of the technical stuff. So basically, off-RL is something that will optimize RL policy entirely from the static offline data set. So when you train this policy, you never interact with the environment. And this is forms a sharp contrast with the online RL. In online RL, exploration plays a very central role, right? But offline RL is everything is about exploitation. So that actually also introduced some of the unique challenges when you are developing an offline algorithm. For example, imagine you are using the Bellman equation to actually learn a value function in the offline setting, and your state action space is partly covered by data. Sometimes some part is not covered by data. Imagine it's like your Q value function is in some cases mistakenly overestimated on some of the parts that not covered by data. And if that happens, your RL agent will mistakenly thought that part will be a good action, and next time it will continue to bootstrap on this erroneously estimated Q values. That will cause severely overestimated Q value estimation. And so that is what the issue we face in the offline RL. So basically, it's like we will face a severe strapping error accumulation in offline RL due to distributional shift that your policy, the distribution of your learned policy is starting to deviate from the data distribution and the cost problems. And this is worsened by the act of maximizing expected return. And so if you look at the literature in the past 5 years, almost about 1,000 papers are comes out about offline RL. And so basically people have figured out different ways to make it work, to make it learning in a stable fashion. For example, sometimes some very straightforward ways, like we add some policy constraints to constrain the learned policy to not deviate too much from the offline data set. And another stream of work is using value regularization, which we modify the value optimization objectives, and so make the OOD part pessimistic, underestimated. So in that case, when we maximize the policy, optimize the policy, we will never go to that OOD places. And some of the early works also use model-based approaches, which the dynamics model as an environment, but we penalize the reward for OOD regions. And some of the latest work is adopt a strict in-sample learning, which we decouple the value learning and the policy optimization, and then both of them strictly with using in-sample data. So all of these methods actually adopt the conservatism and the pessimism. And if you look at some of the benchmarks in offline RL, they seem to perform really well. For example, the D4RL is the most commonly used offline RL benchmarks in the community. And 100 score means the performance level of an online RL agent. You can see in many cases, the offline RL agents are actually catching up with the online RL performance. But is that really the case? Actually not. Actually, we actually found a very negative findings because these benchmarks, in many cases, if you really want to deploy the algorithm into real world cases, and you will find that they hardly provide any reference value because in these benchmarks, typically they are simple toy locomotion tasks, and which is very far from the real world cases, real world scenarios. And also many of these benchmarks, the data is generated using a trained online RL agent, which produce enormously amount of the strongly Markovian data. And that is also different from most of the cases in the world. And also these benchmarks do not consider a lot of issues that is critical for real world deployment, such as the OD generalization, simple efficiency, safety, and also the and also some of in many cases we might have interpreted reward. So if you reduce the size of the training data, and basically you will see most of the similarly performance algorithm actually the performance adjustment drops, and they hardly work in many of the real world cases. And so what's missing? And if we really want to make offline RL work in real world scenarios, basically, of course, we need the algorithm to have high performance, but more importantly, so we need to have these. So we need them to really have high generalization performance. They need to be simple efficient, and they also need to strictly satisfy safety constraints. And sometimes we also need them to tackle with the interpreted reports. And lastly, it's like the offline policy evaluation and offline model selection is also important. And due to the time limit, I will not cover this part. This is actually, I think, is equally hard than developing offline RL algorithm. And so I will mainly talk about these topics. And the first, I think the most important issue when you're trying to deploy offline RL algorithm in real world is generalization. Because as I mentioned before, so most of the current offline RL algorithm actually they adopt pessimism and they trying to contain the policy learning just in the data covered areas. Although they can make the learning policy learning stable, but at the cost of the losing generalization. For example, in many of the cases, you only restrict the policy to be learned in the in sample regions. Basically, then you know nothing about what happens in the OD areas. And because you are optimizing something, it has a high chance that your optimal policy just lie outside your data coverage area. So what do you do? If your policy cannot do a reasonable OD generation, basically that cannot be deployed in real world because bad things happen. And what is more extreme is like in many real world cases, you might have very limited data that is so small that you can hardly train a robust policy. Because when you have limited data, so the data coverage area fully shrinks. Most of your state action space will be OD. So this is actually a very intuitive example, show the over conservatism and the loss of generalization of RL. For example, this is the very simple animate task. For example, the blue part are the data that is of the data. So if we just remove two small regions, in this task, you will see all the existing paradigms of the offline algorithms. They just feel miserably. They cannot solve these problems because they are strictly regularized to not go to OD regions. And to solve this one, basically you need to figure out something to actually make it work. The first thing we are trying to explore we're exploring is actually asking whether we can leverage the good generalization capabilities of deep neural networks. In the supervised learning, so basically we have the neural networks has very remarkable generalization performance, and they train the data and they can reasonably generalize in the OD areas. And so we want to check without data regularization. So basically, can we also have the deep Q function also as reasonable OD generalization capabilities? So what we find is like we actually conducted a simple one-dimensional random walk task, and the x-axis are the states, and the y-axis are the actions, and the white dots here are the data samples. We actually find that it's very interesting that if you use the data set to form a convex hull, basically within the convex hull, you typically get very low approximation error. That means your deep Q functions can generalize reasonably well by interpolated data. But the outside convex hull can get a very large approximation error. That also says its deep Q functions might struggle to extrapolate. This actually agrees with some of the findings in supervised learning. They also find something similar. The deep neural networks can interpolate well, but struggle to extrapolate. And so that actually implies what if we introduce a convex hull-based constraint instead of a data distribution-based constraints? And we're also showing theory actually under mild conditions, and the value difference between an arbitrary sample towards a sample, the closer the sample in the dataset, actually the value difference can be strictly bounded for the interpolated samples, but it can be arbitrarily large for extrapolated samples, depending on distance between these two. And so how to solve this? This means we can actually leverage the dataset geometry and its relationship with the generalizability of deep Q functions. But first, we need to have some kind of distance measure. So to solve this problem, we actually propose a state condition distance function, and which actually allows to output the low values or any state action pair that lies inside the convex hull from the data set, but the high values for extrapolated data. So how this learn actually is quite simple. So imagine you give a state action pair from this set, and you can uniformly sample actions in the action space. That will create a V-shaped curve, distance curve. And then you average all these V-shaped distance curves for every data samples in your data set. And then you will basically learn this function. And it has some very nice properties. The first property is it is always bounds sample to data centroid distance. State condition the centroid of the data set. Another probably is like negative gradient direction of this optimal distance function will always point inside the convex form of the data set. So that makes it an ideal choice for serving as some kind of policy trace. And so actually we can simply add in this constraint, convex policy constraints on top of any online of policy area algorithms, then it becomes a strong outlier with a very good generalization capabilities. And this is the performance of our algorithms. The same task you remove two regions, other methods actually fails, and we still can achieve reasonably success rate by diving from start to the end. So that is for the case when you have the reasonable data coverage. So you need to generalize in some degree. But in many real world cases, like the data is actually much more sparse. For example, this is what you might expect when you want to the very performant of our policy. You might expecting the offline data occupy have reasonably coverage of your action space. This is actually what you get for most of the real world settings, where you only have very little data and very limited data, and the data action coverage is extremely narrow. And so how do we do this? Because this one is like you cannot only rely on data. You need to incorporate something else, something fundamental, something that is invariant. And so to achieve this, basically we'll ask the question, how can we leverage something that is universally held, even for OD regions, that can facilitate possibility, or we can rephrase the problem that what are the universally held invariant information we can leverage in addition to the limited information provided by the data. So what do we find? Something we call time reversal symmetry. So basically, this is a very fundamental and a very ubiquitous symmetry in the physics. So what it says is like the underlying law of physics should not change under the transformation of time reversal. For example, in this agreement, so basically, if you look in the forward direction of time and the reverse direction of time, so their motions seems to be very, very similar because the underlying Newton's law doesn't change. And if you watch the movie Tenet by Christopher Nolan, you will remember the plot where they have two group of people. One is traveling in the forward direction of time, the other is traveling in the reverse direction. And when they have a similar physical faults. And so that's what we find we can leverage to solve our problems even with an extremely small data set. So how to do that? How to incorporate this kind of symmetry into algorithm development. So basically, what we can do is like we can embed a pair of OD dynamics. One is operating in the forward direction of time. The other is operating in a reverse direction time. Actually, they predicting the things they're predicting just forms the opposite value. So basically, they just sum them to zero. So basically, that is the symmetry. And we can also learn a very special model. And by encoding and decoding the data, in the data space, we actually enforce them to satisfy the T-symmetry constraints. Note that the forward dynamics and the reverse dynamics, they need to be OD functions. And so in that case, we can encourage a parsimonious dynamics that can ask for model generalization. So with this, so basically we develop a very highly generalizable offline algorithm. So basically we get the very well behaved and the only generalizable latent representations. And we put all our offline RL learning process inside this latent space. Also, we further enforce the policy learned actions to also satisfy the T-symmetry constraints. We can even do data augmentation by adding some of the T-symmetry consistent noises on the original data. So all these actually helps to promote more generalization and even on small samples. And so these are some results. In the top line are some of the comparative results when we keep decreasing the amount of training data. You can see many of the previous students, the performance scientists are actually decreased dramatically. But our one actually is you only see a mild increase. Sometimes they can maintain almost a full performance, even using maybe 100% of samples. And this is another generalization results. This is a Looker. So basically, for this one, we only keep the low-speed samples and remove all the high-speed samples. But we want the agent to run as fast as possible. And the result is like only our methods can actually the high-speed behaviors, even they never see this on the data. And so the underlying reason is that even regardless of the low-speed data and the high-speed data, they share the same set of dynamics. So that is for generalization. And also, for many real-world cases, we need to strictly satisfy the safety constraints. And so basically, this is a very challenging. And because it's offline RL is already a constraint optimization problem. If you add another set of safety constraints, you have basically you are solving more coupled problems with different set of constraints. So this makes everything very complex, and the learning can be very unstable. So previous methods actually doing this by forcing the soft constraints. For example, the actually learning a cost value function and imported the expectation of this cost value functions below some threshold. This has some problems because in many real-world cases, we want the cost value to be strictly satisfied for any state of the expectation. This one also has a problem that it's like we never go into the accurate feasible region because if the cost signal is positive for some of the outside regions and say for it's 0 for safe places, basically the cost value you learn will always be positive. But the feasibility boundary is actually take the cost value function to be 0. So what we do is like we actually leverage some of the results from the optimal control, which is called Hamilton-Jacobian reachability. So basically, what that says is like even state policy will just look in the long run whether you will end up reaching unsafe state. So that is the reachability level function. We can also solve the optional reachability level function by minimizing our policy. So this will give you a largest feasible region. But this one you can solve it using DP to solve this one. But the issue is like this is only holds for online RL case, and then we actually managed to make it work for offline RL by actually implementing some of the ideas from the example learning methods in offline RL. So in this case, we can actually the very accurate feasible regions just using offline data. And with this, actually, everything becomes very simple. For example, you can just solve simple reward maximization of RL problems in the feasible region. And then for the infeasible region, basically, you do not care about the reward maximization. You just need to get away from this dangerous reason as fast as possible. So you only minimize the cost value. And we can also derive the preventable information that actually easier to solve, and it gives you a closed form solution. So basically, it takes the shape of the behavior policy from the data times a weighting scheme, where it is weighting differently for feasible regions and the infeasible regions. And we can use a powerful diffusion model as a policy, and use a weighting term as a guidance term to actually learn the policy. And the result is actually we can learn very well achieve the safe performance for all tasks in the DSL benchmark, and using only a single set of parameters. And we can also use this methods to save offline IOS imitation percent. So I will see this. And so we have some of the new machineries. So that's next. We actually use this type of methods to solve another real world district control problems. This time is like we actually use OpenRL to optimize the cooling system of the data centers. The current data centers industry is expanding rapidly, and the big data center actually consumes 100 megawatts of electricity every year. 30 to 40% of them are spent on the cooling systems rather than servers. And the problem is also very complex. We cannot do installation, or installation is very inaccurate. So we also use the OpenRL. So this one actually we use some of the previous TCP realized OpenRL. I introduced add some knowledge. For example, we abstract the server layout into the graph structure, and then we structurally build a encoder to actually capture the dependency of the data. And everything else is similar to the previous high generation algorithm. And we actually tested on the real world data centers with 2 different server rooms. And this has been safely running for almost 2,000 hours in closely controlled mode, which is a much solid work and what I introduced. And we also build a small scale data DC test lab environment to test different versions of our algorithms and do the vision and comparison. And so this is the results. And so basically you can save up to 20% of the energy for the systems, and just using maybe time of 300,000 samples, historical samples from the data center. And also we have the abstract control, and on the right are the control strategy and the results for our OpenRL methods. So you can see, although the training data is all based on the conventional district control controllers, the data actually learn very different control pattern theories, and also they choose a much better regulated temperature field for inside the server. And also it's like we have conducted ultra long term experiments that ask our algorithm to running consecutively for 14 days. And then we see that actually our methods actually perform even better when the server loads actually gets higher. But you do not see this on the carry controllers. And also it's like we also tested by actually different numbers of these units, and also it also confirms the effectiveness of this method. So the more we control, the higher energy saving we can get. So this is the last slide of my talk today. So basically, I think the OpenRL is developing ultra fast in recent years, and also starting to impacting other areas. At least 4 or 5 years ago, I never imagined that we can do close control directly using OpenRL agent. But right now, with the OpenRL, using OpenRL policy to close control for thousands of hours, that is a huge progress. But we still have a lot of problems to solve. So I think increasing the robustness of the generalization are the key. And still there's a lot of investigation. And also, I think it's very important to move away from toy unrealistic our benchmarks, especially for OpenRL study, when we need to focus more on real world tasks or scenarios. Thank you, everyone. I'd also like to thank my current student.
Wonderful, thank you very much. There's a time for some questions.